Welcome back to the penultimate session for our course on Introductory Materials Informatics. So we will continue in the same vein as the last couple of lectures where we first talked about combinatorial materials processing and then we discussed high throughput materials characterization. And both of those approaches are designed towards rapidly generating a lot of experimental data. And this becomes really important if the data that is already available to you in the literature is relatively sparse and you need to generate a large chunk of data in order to build robust machine learning models. Now, what happens if you do not have access to those high throughput methods, or maybe you do not really have a suitable high throughput method for the type of work that you are trying to do? Sometimes it can also happen that certain regions of data can remain inaccessible from an experimental perspective, meaning that you have limitations in what parameters you can actually vary while doing the experiments. So in those cases where there is absolutely no way in which you can access experimental data or generate experimental data, the only available approach for us would be to create synthetic data and then work with synthetic data sets. So with that in mind, today we are going to discuss a little bit about how we create synthetic data and how we integrate synthetic data in the materials informatics pipeline. So first of all, let us understand what is it that we really mean by synthetic data. So supposing you in your parameter space, you have data that looks like this. You have a cluster of data over here. You have another cluster of data over here, but then these two clusters are spaced fairly far apart, and so it becomes difficult to actually figure out how this interim space would get filled. So this is the region where we have a gap, and then we need to fill this gap. So the question is, how do we actually go about filling this gap? So what we then do is we try and fill this space by using synthetic data. Now, one has to understand that use of synthetic data is not really a proper substitute for the actual real-world experimental data that is often gathered in a very painstaking manner. Remember, the proof of the pudding is when you eat it, and really there is no substitute for the experimental data. That is the ultimate test for any theory. And so what we are doing when we use synthetic data is simply use some sort of a stopgap type of approach. So whenever there are gaps in the data, if your data set is especially sparse, which is unfortunately a common issue in materials, or if you see some amount of imbalance in the data, that is where people will try and fill in with the synthetic data. So we have actually come across some of those examples before when we were talking about microstructure reconstructions, where we were effectively generating new microstructures based on the probability distributions of the microstructures that we already had in our data set. Or you could generate the data from performing some high quality simulations. So whatever the case, if this is the entire funnel of data that you've got and your experimental data is present only in a small amount, then you really do not have much options other than using synthetic data, generating synthetic data and using synthetic data. So what are the methods of synthetic data generation? By and large, we can classify that into 4 different types. So first would be a simulation based approach. So here you will be using techniques like density functional theory or molecular dynamics or phase field modeling, that type of work. Second is to use an AI model in order to generate the data. Essentially, you will be using some sort of a generative AI, whether that's a GAN or VAE or a diffusion type of model. The third one is to use some form of a rules-based and physics-inspired models. So something like a cellular automata type of simulation would really be useful over here. If the rules of the process or the physics of the process is really well understood and the process is extremely hierarchical, then you can simply create a rules-based simulation and then get the data from there. And finally, you can augment the data. So when we talk about augmenting the data, what we are essentially saying is we will be injecting some noise, we will be doing some sort of a data transformation. So in that sense, what we are doing is we are creating an additional volume of data which is not entirely new, which is actually coming from the sparse data set that we have. So we are using the initial sparse data that we have got almost as a seed, and then we are augmenting that. So all of these processes can be utilized in order to create synthetic data. So let us go through them one by one. So let's first take a look at the simulation based methods. So the first one that we can use is the calculations using the density functional theory. So density functional theory is essentially some sort of a quantum mechanical method, and then essentially what we are doing is we are coming up with approximate solutions of the Schrodinger equation. The main challenge with working with the Schrodinger equation is if you are looking at something like a hydrogen atom, it is easy to work, maybe with helium as well, but then once you get into the many body problem, then the computational challenge scales exponentially, and that is where getting an exact solution becomes difficult. And that is why people have come up with different types of approximate methods to solve the Schrodinger equations, and all of that falls under the ambit of density functional theory. Now, the advantage that we have got nowadays with extensive computational power is that we can actually start creating fairly large simulation cells, introduce some defects, and so it's not necessary that when we do this type of calculations will be constrained only to perfect crystals. We can even look at the effect of defects and so on and so forth. Nowadays, people are also using the density functional theory coupled with molecular dynamics type of approach to come up with ab initio molecular dynamics. And those typically works with hundreds and hundreds of atoms, fairly large simulation cells. So DFT is gaining ground as a way of creating synthetic data, especially because nowadays we have got fairly validated potentials that can be used to do this type of calculations. Now, one of the things you do in the density functional theory is you create a particular crystal structure, and that crystal structure is associated with a certain chemistry, and therefore this becomes an awesome method if you want to create synthetic data as far as the intrinsic properties are concerned. Yet another approach for creating synthetic data comes in terms of the molecular dynamic simulations. And so here what you are doing is you are using a pair potential, and that pair potential is essentially an approximation of how the two atoms are going to interact with each other. So we are not getting into the quantum mechanics directly, but then the implicit understanding is somehow the pair potential that we are using for the pair of atoms that we are trying to model is more or less capturing the hidden quantum mechanics in there. Unlike the density functional theory, where the simulation cells tend to be of the order of tens or hundreds of atoms, with molecular dynamic simulation we can go to much larger system, and easily we can handle lakhs of atoms, sometimes even millions of atoms. So once you know the pair potentials, doing the molecular dynamic simulation basically requires you to iteratively solve the Newton's laws of motion. So essentially this entire simulation is built around solving Newton's laws of motion. So if you have a potential given by u, then you can simply take the derivative with respect to the separation, and that will give you a measure of the force which is acting on the atom. So once you know the force, now you can start solving the Newton's laws of motion. This type of method is an excellent way if you want to look into atomic scale processes. So things like modeling of diffusion or maybe viscosity in case of fluids, formation of clusters in the liquid state, all of these things can be studied with molecular dynamic simulations. The third rather important technique that I would want to bring up over here is that of phase field modeling. So phase field modeling is again going up the length scale a little bit. When we started our discussion talking about density functional theory, we were looking at the level of electrons. As we moved on to molecular dynamics, instead of looking at the electronic structure, we started looking into the atomic scale processes, and then as you scale up further to phase field type of methods, now you are starting to look at the microstructure of the material. So if someone is doing microstructure informatics and they do not have a big enough library of microstructures with them, the experimental microstructures with them, then they can simply dive into phase field modeling and start generating synthetic microstructures from there. So phase field modeling is quite well ingrained with thermodynamics, and it requires the solution of the Allen-Kahn or the Kahn-Hilliard equations. And essentially what you are really solving for is the order parameter that tells you whether one phase is present or the other, as well as the nature of the transition or the nature of the interface. So one of the advantages of using a phase field type of technique is now you can look into how the microstructures will evolve when the conditions are different, because you can start programming in the type of constraints under which you want to look into the microstructural evolution. The second class of methods that can be used for generating synthetic data is the use of generative models or the use of AI. The generative models that are typically used are things like the generative adversarial networks or the variational autoencoders and so on. So we'll just talk about the GAN because that is actually finding a lot of traction nowadays in the world of materials. The initial idea for GAN or the generative adversarial network was given by Goodfellow, and this was way back in 2014. So it's about 10 years now, not very old type of technique. So here the idea is if you're given a training set, the adversarial network is going to generate data where essentially the statistics of the data is going to be similar to what you had in your original data set. So there are a number of well-trained such models, and one of them which I wanted to highlight is this model called SliceGAN. So SliceGAN, until now it's an open source model, so you can actually look it up, import it in your Python framework and then start working with it. The idea behind SliceGAN is that you can train a model using lots and lots of images, and then you can use that in order to generate newer images. So if you apply it for microstructures, essentially what you do is you will start with your original image. You will do a little bit of pre-processing in terms of thresholding the image and so on. You may have to do a little bit of in-painting after the thresholding is done. So essentially in-painting means you will end up with some missing pixels which you will have to paint in or which you will have to substitute, and then you can do a 3D generation. So basically what this type of model does is it allows you to start with a 2D image and then helps you create a 3D image. Now depending on whether you have a very highly textured material or whether the texture is not that prevalent and you are dealing with the isotropic conditions, the number of initial images that you need in order to generate a accurate 3D image is also going to be different. If you're working with an isotropic material, in principle you could even start with a single image, and that can help you do some kind of a 3D reconstruction. So as you can see over here, the first one refers to a dendritic microstructure, and then if you look at this image quite carefully, you will see a bunch of needle-like structures which are the different dendrites. The second one, on the other hand, is a porous structure. So when you do the 3D reconstruction, you can see that you are also having a network of pores in the particular structure. The link to the original paper related to SliceGAN is given over here, and then this one is the reference from where we pulled up these two images where they have actually used SliceGAN in order to generate entire library of 3D microstructures starting with 2D images. Then you've got rules-based and physics-inspired type of models. Cellular automata type of model would be a prime example in this case. So here what we had done was we were trying to implement certain hierarchy of rules in order to model the oxidation behavior. So essentially what you can do in processes where you have a reasonably good understanding of the underlying physics and the chemistry is you can come up with a set of rules. So for instance, when you are trying to do an oxidation model like this, you might come up with a set of rules that, let us say you are working with nickel aluminide. The moment nickel or aluminum from there comes in contact with the atmospheric oxygen, it is going to oxidize and form Al2O3. Then you can come up with a second rule that if you have nickel oxide sitting next to aluminum, then it is going to get reduced, resulting in the formation of alumina and nickel. And this comes from the fact that the alumina line lies lower in the Ellingham diagram. So there is a physical basis for coming up with this rule. Similarly, one can also look at diffusion from a rules-based process. So for instance, supposing you already have an oxide scale that has formed and you are trying to look at the oxygen or the aluminum cation diffusing through the scale, you can actually use the experimentally measured diffusivities in form of rules, or rather in form of probabilistic rules, that will govern how the diffusion process will take place and how fast the oxygen or the aluminum is going across the scale. So when you use a process like this, you can again start modeling things like the mass change, etc., which is something which can be measured and validated experimentally. So use of cellular automata can be quite useful when you are looking at processes like oxidation or recrystallization or grain growth. This type of models are fairly well developed nowadays. In terms of increasing the volume of your data by doing data augmentation, the standard methods would include rotation, flipping, scaling, or maybe injecting some noise artificially into your data. So this would be actually a very nice way of augmenting the microstructural data sets, because all you need to do is come up with some sort of a rotation for the microstructures, maybe add some noise in the microstructure and so on. Now, of course, there are certain challenges associated with it, especially when you are working with the microstructure. You might be having microstructural defects, and representing them may be a challenge. And that is because, supposing you are not observing a microstructural defect in a single microstructure, it doesn't really mean that you don't have a defect. But at the same time, if you're having a defect in a microstructure, it doesn't mean that you look anywhere and around the same place you will be having a defect. So the challenge with data augmentation really comes from the statistics of the process, how well you are able to capture the statistics. Some of the things, especially if they tend to be some sort of a rare event, would be very difficult to capture in a statistically accurate type of manner. And that is where the typical data augmentation type of techniques will fail. So over here, this is a flow sheet from this paper by Ma, which looks at data augmentation specifically in case of microstructures for doing some sort of a data mining. And again, the idea over here is initially you will start with the real images, which you will be labeling, and then from there you will also be able to generate some simulated images. Now, once you generate a good volume of synthetic data, there are certain integral challenges for assimilating this data within your materials informatics pipeline. So this graphic kind of captures the idea that when you have got the experimental data over here, they may be sparse, but that is the data which you will deem as trustworthy. Whereas your synthetic data might be generated quite easily, but then these are not trustworthy. Even if you're trying to fill in the gaps, there is always a chance that the synthetic data is going to mislead you. There is going to be a certain risk of bias. And this bias is going to be quite significant if you structure your data set in such a way that the synthetic data is actually dominating the experimental data. So what really matters is that you should do a proper calibration and validation of the model, and there has to be a proper balance between the experimental data that you have got and the synthetic data that you've got. Now, supposing the model for generating the synthetic data is excellent, then of course one can generate more of the synthetic data, even if your experimental data set is sparse. But really what matters is you should be able to have an idea of how good your models are for generating the synthetic data. That is really the key over here. So just to give you an example, I will highlight a paper over here by Professor Krishanu Biswas, where he has actually used synthetic data in developing a machine learning model for predicting the type of phase that will form in case of a high entropy carbide. Now, high entropy carbides are not very common to find. You do not have a huge volume of experimental literature on the high entropy carbides, and therefore there is definitely an accurate paucity of data in there. So what they did over here is they looked at the experimental data they had, and they created a structure plot, and from there they were able to come up with some sort of a sorting criteria for a couple of different types of high entropy carbides, namely a quaternary carbide and a quinary carbide. So what they found was, when the difference in the Pauling electronegativity was within a certain value, and the formation enthalpy was within a certain value, quaternary carbides seem to form, Whereas when you look at the quinary carbides, the electronegativity range does not really change, but then the formation enthalpy range over which it forms is changing. And as you can notice, in case of the quinary carbides, you can actually go to slightly higher values of the formation enthalpy. So what happens when you add in synthetic data can be seen from this plot over here. So before using the synthetic data recipe, this is how the plot looked. And then after adding the synthetic data recipe, you can see that a bunch of new data points have been added, and even the original clusters have been populated a little bit. But what I really want you to understand from over here is the synthetic data essentially filled in the gap over here and added just a little bit to the volume of the data, but not a huge amount. You can see that here also you have got some amount of synthetic data coming in. Here you have some amount of synthetic data coming in, but the amount of synthetic data is not a overkill, and there is a proper balance between the experimental data and the synthetic data. So this is one of the things that you can actually, you should actually keep in mind when you are working with synthetic data. And again, for more details on using synthetic data in machine learning, I would strongly recommend you to take a look at this particular paper over here. Now, even if you use synthetic data, it has to be validated properly, and so you have to come up with proper validation strategies. And so what that means is when you are cross-validating, you must be cross-validating with experimental data, and not just the experimental data which was part of your original data set, but unseen experimental data on which the model had not been trained. So the idea over here is you have your sparse data, you are then adding synthetic data to it. Now you have a larger data set and you are training your model on it. So when you develop a model like that, you must validate it with unseen experimental data. That's always going to be a good way of checking whether you have got synthetic artifacts in your data or whether your data set was robust. The other thing that one can do is, if you can team up with a domain expert, or if you are yourself a domain expert, then you can look at the predictions and answer the question, does it make sense? If it does, maybe you can trust it. If it does not, then you might actually have to rethink your machine learning process. Uncertainty quantification is again another thing which is very important. So if you are using some sort of a probabilistic type of approach, it may be a good idea to work with the entire distribution rather than a single value. Or if you can come up with ensemble type of learning, that is again something which is going to minimize the uncertainties. Then again, you have got the dropout methods. All of these were discussed in the first part of the course, and all of them can actually be useful in helping you handle the synthetic data. So there you have it in a nutshell. You use synthetic data when the amount of experimental data you have got is quite sparse and you need to augment your data set. Be aware that the quality of your model really depends on the quality of your data. So if you are getting your synthetic data from robust models, chances are you will be able to build a trustworthy machine learning model. Otherwise, you have to be very careful as to how you use your data. So it is always going to be a balance between how much of synthetic data you can add and how much of experimental data you have got. So it is up to you as the person developing the model to strike this balance and ensure that you end up with a machine learning model which is at least somewhat trustworthy. Remember, synthetic data is really good for augmenting your data set, but then it is never ever going to be a substitute for the experimental data. So with that, now you have an overall picture of how you can augment your data sets. We talked about the combinatorial materials processing in order to generate a library of compositions and alloys. And then we talked about high throughput characterization, which will allow you to characterize a bunch of different chemistries very rapidly, or maybe even a single chemistry under a host of different conditions very rapidly. And final piece of the puzzle was, if you cannot absolutely do the experiments, whether the traditional experiments or the high throughput experiments, then you can to some extent start relying on the synthetic data. But just be aware about how you are using the data and what implications that has on the trustworthiness of your model. So with that, we are going to stop for now. Thank you very much for joining.